Let us now discuss about the self-induction in details. So today we will try to learn the concepts of self-induction. Okay, so first of all, I will write some introduction about the self-induction, then some mathematical expression for self-inductance, and finally we will try to find the self-inductance of some standard geometries. So first of all, it's the self-induction. So I write it in this way: self-induction is of equal importance. Self-inductance is of equal importance in a single circuit. Actually, in inductance we used to say the effect of the magnetic field on another circuit. আমরা সবসময় যখন বুঝিয়েছি self induction তোমার Faraday's induction, whenever we have discussed about Faraday's induction, we have said that suppose this is a coil and a magnetic field is moved in its vicinity. So এটা হচ্ছে একটা coil আর এটার আশেপাশে একটা magnetic field কে আমরা মুভ করাচ্ছি. Then what is the effect of this magnetic field on this particular circuit? Right. So effect of one on another. But today I am discussing self-inductance. Self, the word self, you know that in itself, in the body itself, মানে যে বডিটা কনসিডার করেছি, the body that I have considered, that body itself, সেই বডিটার মধ্যকারে, so within that body only. That is what do I mean by self-induction. So let us try to discuss about it in details. So self-inductance is of equal importance in a single circuit. Is of equal importance in a single circuit. When a current flows in the circuit, comma, it produces a magnetic field. It produces a magnetic field around the surrounding space. When a current flows in the circuit, it produces a magnetic field around the surrounding space, and so there will be a flux linkage, and so there will be a flux linkage, with the circuit. So there will be a flux linkage with the circuit. If the current through the circuit varies with time, let me first write, then I will explain. If the current through the circuit varies with time, comma, then what will happen is that then there will be a rate of change of of magnetic flux, then there will be a rate of change of magnetic flux in it, which give rise to an induced EMF. Which give rise to an induced EMF. The direction, you know about the direction. The direction of the induced EMF is such that it opposes the change of current. In the circuit. Right. So now you try to understand this. এই পুরো ঘটনাটা বোঝার চেষ্টা করো. So whatever I have written, let me try to explain it. Suppose this is a circuit over here and a current is flowing through it, right? So এটা একটা সার্কিট যেটার মধ্যে দিয়ে কারেন্ট যাচ্ছে, some current is flowing through it. Now as some current is flowing through it, from the Biot-Savart's law you know that definitely there will be a magnetic field over here. Magnetic field means there are some magnetic lines of force crossing through this conductor. এটা বোঝা গেল তো কি বলছি আমি? So there is no magnet over here. So এখানে কোনো magnet আলাদা করে নেই. There is no separate magnet. So whatever I am trying to say is that this is a circuit, this is a coil and some current is flowing through it. এটা একটা coil এবং এটার মধ্যে দিয়ে current flow করছে. Some current is flowing through this particular coil. Now what actually happen is that when the current is flowing through this particular coil, according to the Biot-Savart's law, some magnetic field will be created in the vicinity of this coil. এই কয়েলের চারিপাশে একটা ম্যাগনেটিক ফিল্ড তৈরি হবে। Now corresponding to this magnetic field there will definitely be a flux এবং এটা corresponding একটা flux থাকবে। So this is the flux that passes through that particular circuit which I have written. দেখে নাও, when a current flows in the circuit it produces a magnetic field and so there will be a flux linkage with the circuit. So these are the flux. Okay, you have some flux over here, right? Now suppose the current in the circuit varies with time. So if the current in the circuit varies with time, the current increase or decrease with time, so it is not a steady current. So as the current varies with time, so definitely the magnetic field will also vary with time. Current যদি vary করে তাহলে magnetic fieldটাও vary করবে, and at the same time this flux will also vary. Is it clear to you? So as the current varies, the magnetic field also varies, and as a result of it the flux also varies with time. And now you definitely know that wherever there is a rate of change of flux, that is d phi dt is now what? It is definitely non-zero because this flux is a function of time. A flux the time er function, so definitely this flux is non-zero. So that is why you know that there will be some developed EMF. তাহলে এখানে একটা EMF develop করবে which gives rise to an EMF. So which gives rise to an EMF. ঠিক আছে? So this is how an EMF is generated in the circuit, and this is known as the self inductance, এবং এটাকে আমরা বলে থাকি self inductance. Self inductance means the effect of one on itself, the effect on itself, নিজের মধ্যে যে এফেক্টটা তৈরি করে, so that effect is known as self inductance. There is another effect which is known as the mutual inductance. Mutual inductance means the effect of one on another. The effect of one on another is called mutual. আর effect self inductance মানে the effect of one on itself. তাহলে এভাবে হলো হচ্ছে তোমার EMF. So that is how a EMF is generated in the circuit. মানে অরিজিনাল কারেন্টটা তো আছেই, there is some original current in the circuit. দেখো অরিজিনাল কারেন্টটা কিন্তু আছেই, there is some original current. In addition to the original current there is some other current, and that is known as the induced EMF. Now this type of effects you try to see somewhere else. এই ধরনের এফেক্ট কিন্তু আমরা দেখতে পাই in our regular day to day activities. You come across these activities. Where do you see this? আমি দু একটা এক্সাম্পল বলছি। In a stabilizer, if you have a stabilizer, stabilizers are basically associated with the refrigerator. বাড়িতে ফ্রিজ থাকলে অনেক সময় স্টেবিলাইজার থাকে। Then the light of your television, as soon as you switch on or switch off your television, টিভি যখন চালানো বন্ধ করে একটা লাল বা সবুজ লাইট জ্বলে ওঠে, a red or green light glows up. Okay, light of any type of charger, laptop charger, mobile charger, there is a light. তুমি দেখবে ল্যাপটপের চার্জার, particularly ল্যাপটপ চার্জার, there is a light, blue, green, red, এরকম লাইট থাকে ল্যাপটপ গুলোর মধ্যে। পেয়েছো না দেখতে, চার্জারে লাইট থাকে। আচ্ছা এবার আমাকে বলো, এটা কখনো কি দেখেছো? হ্যাভ ইউ এভার সিন দ্যাট ইউ আর সুইচিং অফ দ্য চার্জার বাট স্টিল দ্য লাইট গ্লোজ ফর ফিউ সেকেন্ডস? দেখেছো? এভরিবডি হ্যাভ সিন ইট, এভরিবডি হ্যাভ সিন ইট। তুমি যখন ইমিডিয়েটলি যখন ধরো ল্যাপটপটা চার্জ করছো, ইউ আর চার্জিং ইউর ল্যাপটপ অর ইউ আর চার্জিং ইউর মোবাইল, সো ইমিডিয়েটলি ইফ ইউ সুইচ অফ দ্য চার্জার, তুমি চার্জারটা যদি সঙ্গে সঙ্গে বন্ধ করে দাও, if you switch off the charger the light doesn't glow up immediately. লাইটটা কিন্তু সঙ্গে সঙ্গে কিন্তু জিরো হয়ে যায় না, আলটিমেটলি জিরোই হবে, the light goes to zero, but it takes some time for the light to go to zero. It takes some time for the light to go to zero. You have, everybody of us has noticed this in our lifetime. আমরা দেখেছি এই ঘটনা। So the reason behind this is nothing but self induction. এটার কারণ কিন্তু self induction. What is the explanation? The explanation is there is some current in the circuit. চার্জারের মধ্যে কারেন্ট আছে, ইউ সুইচ ইট অফ। সো অ্যাজ সুন অ্যাজ ইউ সুইচ ইট অফ দ্য কারেন্ট ট্রাইস টু ডিকে, কারেন্টটা কমে যাওয়ার চেষ্টা করছে। সো ইনিশিয়ালি দেয়ার ইজ সাম কারেন্ট, দেয়ার ইজ সাম ম্যাগনেটিক ফিল্ড। নাও অ্যাজ ইউ সুইচ ইট অফ, অ্যাজ ইউ সুইচ ইট অফ, তখন কারেন্টটা কি করবে? দ্য কারেন্ট উইল ডিক্রিজ, কারেন্টটা কমে যাচ্ছে। অ্যাজ সুন অ্যাজ দ্য কারেন্ট ট্রাইস টু ডিক্রিজ দ্য ম্যাগনেটিক ফিল্ড ট্রাইস টু ডিক্রিজ, ম্যাগনেটিক ফিল্ড কমার চেষ্টা করছে। অ্যাজ দ্য ম্যাগনেটিক ফিল্ড ইজ ট্রাইং টু ডিক্রিজ দেয়ার ইজ দ্য রেট অফ চেঞ্জ অফ ফ্লাক্স ইন দ্য সার্কিট, সার্কিটের মধ্যে একটা ফ্লাক্স চেঞ্জ আছে, বুঝতে পারছো? So as soon as the current is switched off, the magnetic field is also decreasing. As soon as the magnetic field is decreasing, the flux is also decreasing. মানে কি, there is a change of flux. ফ্লাক্সটা চেঞ্জ করছে টাইমের সাথে, ডিক্রিজ করছে, the flux is decreasing. So the flux is decreasing with time. So that means that there is some rate of change of flux. ফ্লাক্সের একটা চেঞ্জ আছে, and any rate of change of flux is what? That is induced EMF. Okay, and according to Lenz's law, this EMF should oppose its own cause. এই যে ইএমএফ যেটা জেনারেট হলো, দিস ইএমএফ উইল অপোজ ইটস ওন কজ, ওর নিজের কারণকে অপোজ করবে। হোয়াট ইজ দ্য কজ ওভার হিয়ার? ইট উইল অপোজ দ্য কজ। হোয়াট ইজ দ্য কজ? কজ ইজ সুইচিং অফ দ্য লাইট। সো ইট উইল অপোজ দ্য কজ। অপোজ করা মানে কি? ইট উইল অপোজ দ্য অফ। তাহলে এই অফ করাটাকে অপোজ করবে, তার মানে কি হবে? ইট উইল ট্রাই টু রিমেন অন। অপোজ করা মানে কি, হোয়াট ডু মিন বাই অপোজ? রিপেল করছে, যা ঘটনা ঘটছে তার অপোজিটটা করার চেষ্টা করবে। ইট উইল try to reflect the opposite. So you are switching off the circuit, so it will try to remain switch on. So that's why the light glows for few seconds. এখন তুমি বলতে পারো স্যার তাহলে সব সময় কেন অন থাকবে না? Why will it not be on for the entire time? Because ultimately the current drops to zero. Ultimately current drop করে যাবে, and the flux আমি কি বলি, the flux is dropping down, ফ্লাক্সটা কমছে, and at a particular time the flux will be zero. একটা সময় ফ্লাক্সটা itself zero হয়ে যাবে, the flux itself will be zero. So then there cannot be any change. So ultimately the EMF drops to zero. ফাইনালি ইএমএফটা জিরোই হবে, বাট ওটা চেষ্টা করবে, ইট উইল ট্রাই ইটস লেভেল বেস্ট টু অপোজ ইটস ওন কজ। এন্ড হোয়াট ইজ দ্য কজ? দ্য কজ ইজ সুইচিং অফ। It will oppose it, that means it will try to remain switch on. Okay, so please try to do it with your chargers. নিজের চার্জার দিয়ে একবার করার চেষ্টা করো। Okay, now you will see that in some chargers the light glows off faster. কখনো তাড়াতাড়ি immediately তো কোথাও glow off করবে না, it will not be the light will not glow off immediately as you switch it off. অফ করার সঙ্গে সঙ্গে হবে না, কোন চার্জারে দেখবে একটু তাড়াতাড়ি হয়। In some chargers the light glows off faster, in some chargers it takes some more time. So now who is responsible for this? In some chargers the light glows off faster, in some chargers the light glows off slower. Now who is responsible for this? The property that is responsible for this is called self inductance. So যেই প্রপার্টি এই কারণে এটার জন্য রেসপন্সিবল, সেই কারণটাকে বলে হচ্ছে ইন্ডাকটেন্স, সেলফ ইন্ডাকটেন্স। এর বাংলা নামগুলো আমি জানি না, আই ডোন্ট নো দ্য বেঙ্গলি নোমেনক্লেচার অফ দেম, সো আমি এর বাংলা আমি বলতে পারবো না। সো যারা পড়েছো তারা খুঁজে নেবে হায়ার সেকেন্ডারি বই থেকে। সো বিকজ অ্যাজ আই অলওয়েজ সাজেস্ট গো থ্রু দ্য হায়ার সেকেন্ডারি টেক্সট বুক, সো ইউ প্লিজ ফাইন্ড দেম ইয়োরসেলফ। অ্যাকচুয়ালি ইট ইজ ডিনোটেড বাই ক্যাপিটাল এল, সো আই হোপ দ্যাট ইউ নাও রিমেম্বার। তোমার হয়তো মনে পড়েছে তুমি বাংলায় কি বলেছিলে, আই ডোন্ট নো ইট অ্যাকচুয়ালি। So the direction of the induced EMF is such that it opposes the change of current. Okay, এটা তো হয়ে গেল। Okay, এইবারেতে the flux linked you always know, the flux linked is always proportional to the current in the circuit. The flux linked is always proportional, the flux linked is always proportional to the current, in the circuit. The flux linked is always proportional to the current in the circuit, that is flux phi is proportional to I, right? Because more the current, more the magnetic field, more the flux. Very easy, তাই তো? কারেন্ট যত বেশি, ম্যাগনেটিক ফিল্ড তত বেশি, ফ্লাক্স তত বেশি। ওকে, so flux is proportional to this current. So in order to remove the proportionality you bring a constant, and this constant is known as L. So L is called the self inductance of a coil. L is the self inductance of the circuit. Self inductance of the circuit. Okay, now depending upon the self inductance the light will glow up faster or the light will glow up slower. So লাইটটা তাড়াতাড়ি বন্ধ হবে না দেরিতে বন্ধ হবে সেটা ঠিক করবে হচ্ছে সেলফ ইন্ডাকটেন্স। সেলফ ইন্ডাকটেন্স will decide that. So that is how self inductance is important to us. So flux phi is equals to Li for a single coil or for a single circuit. Flux equals to Li. What is the definition of L? You can define L in different types of ways. So L কে অনেক ভাবে ডিফাইন করা যায়, আমি একটা করার চেষ্টা করছি। If I equals to 1, then you understand that L equals to 5. What does it mean? If I equals to 1, then L equals to 5. What does it mean? That is, the self inductance is defined as the self inductance is defined as the flux linked with the circuit. Self inductance is defined as the flux linked with the circuit when unit current passes through it. When unit current passes through it. Okay, self inductance is defined as the flux linked with the circuit when unit current passes through it. So যখন ইউনিট কারেন্ট পাস করবে সেটাকে আমরা বলবো। ঠিক আছে, আচ্ছা, there is another definition, one more definition. দেখো এখানেতে there is another definition of this inductance. We know induced EMF E equals to dphi dt. I don't use the negative sign, that's just to remember that it opposes its own cause, so I don't use the negative sign over here, just আমি লিখছি E equals to dphi dt. তাহলে আমি নিশ্চয়ই লিখতে পারি this one to be ddt of, in the same line I can write it ddt of flux phi মানে হচ্ছে li, or I may write L di dt, লিখতে পারি induced EMF equals to L di dt. এইবারেতে এখানেও যদি এই কাজটা করি, if di dt I put it to be 1, if I put di dt to be 1, then L is equals to E. So another definition develops from here. তাহলে এখান থেকে আরেকটা definition চলে আসবে. What is the definition? So the self inductance can also be defined. The self inductance can also be defined. The self inductance can also be defined as the what? The self inductance can also be defined as the EMF induced in the circuit. EMF can be defined as the EMF induced in the circuit. EMF induced in the circuit when? EMF induced in the circuit for unit rate of change of current. For unit rate of change, for unit rate of change of current in it. So these are the two definitions of self inductance. So এই দুটো হচ্ছে self inductance এর definition যেটা তুমি এখান থেকে শিখবে, বোঝা যাচ্ছে তো? So are you finding it interesting that what is self inductance, how it is developed, কি করে develop করছে self inductance টা? So all these are quite interesting to us. So this is how we define the self inductance. We define self inductance. Now let us try to calculate the self inductance of two geometries. এবার আমরা একটু চেষ্টা করি দুটো geometry self inductance calculate করতে. Let us try to calculate the self inductance of two geometries. What are those? What are the geometries that whose self inductance we want to calculate? একটা ধরো আমি হেডিং দিচ্ছি self inductance of a coil. Self inductance of a circular coil. Of a circular coil. We will do a very elementary treatment. আমরা খুব elementary treatment করব. Suppose this is my okay, এখানে লিখে রাখো খালি, দেখো consider a circular coil. Consider a circular coil of, consider a circular coil of capital N. Consider a circular coil of capital N number of turns. Consider a circular coil of capital N number of turns carrying current I, carrying current I, and consider a circular coil of radius A having n number of turns and carrying current I, having n number of turns and carrying current I. Consider a circular coil of radius A having n number of turns and carrying current I, এবং এর কারেন্ট হচ্ছে I. So এই হচ্ছে তোমার পুরো কয়েলটা. So this is your coil. Is it clear? এবার এই কয়েলটার মধ্যে কতটা সেলফ ইন্ডাকটেন্স ডেভেলপ করেছে. What is the self inductance developed in the coil? So as the coil is carrying some current, so there will be some magnetic field. So you consider a coil like this. এরকম আমি কয়েলটা নিলাম. This is my coil of radius A. আচ্ছা, magnetic field at the center of the coil. Magnetic field at the center of the coil. What is the magnetic field at the center of the coil? So the expression that you know, so mu 0, as far as I remember, the expression was mu 0 I by two R. The expression is mu 0 I by 2R. এটা ছিল তোমার এক্সপ্রেশনটা. This was the expression, magnetic field at the center of the coil. But if it has n number of turns, so then that should be multiplied by n. So mu 0 ni. So আমার এখানে n লেখা উচিত because there are n number of turns of this particular coil. Okay, so this is the magnetic field at the center of the coil, right? This is the magnetic field at the center of the coil. And we make an assumption over here that we consider the magnetic field to be same throughout this plane. Actually, এই যে magnetic field যেটা তুমি বের করেছো, the magnetic field that you have found, it is at the center of the coil. But you see that you don't need the magnetic field not only at the center, you need the magnetic field not only at the center but all other points of it. So তোমার প্রত্যেকটা পয়েন্টে magnetic field লাগবে, and definitely the magnetic field is not same at all the points. But here we assume for our simplicity in the treatment that the magnitude of the magnetic field is same throughout. But I repeat once again, this is not absolutely true. But if I want to find the magnetic field at different points, so then that would be a very non-trivial task. যে কোনো arbitrary point magnetic field expression আমাদের কাছে নেই from the Biot-Savart's law. From the Biot-Savart's law, I don't have the expression of magnetic field at any arbitrary point. Okay, I don't have the expression of magnetic field at any arbitrary point. But whatever I have is that the magnetic field at the center. Is it clear? So the magnetic field at the center of the coil is this one, and it is assumed to be uniform throughout the plane. And it is assumed to be uniform throughout the plane. Throughout the plane of the coil. Because our main goal is not to find the magnetic field but to show you that what is the expression of self-inductance and how to calculate self-inductance. Because আমাদের actual উদ্দেশ্যটা এখানেতে magnetic field বের করা নয়. You have to understand the goal over here. So it is to find the expression of self-inductance. So that is why we are doing so. And if you assume the coil, the radius of the coil to be very small, so then this assumption is perfectly true. And that is what we are doing also. It is assumed to be uniform throughout the plane of the coil. Because this much assumption will help us to get some good result. It is assumed to be uniform throughout the plane of the coil. আচ্ছা, এবারে flux linkage কত আছে? So flux linked with the coil. So flux links, that is phi, is definitely, you know the formula, that is NAB. So the flux linked with the coil is NAB. ঠিক আছে? That is the next idea. The flux linked with the coil is NAB. Flux linkage টা হয়ে গেল আমাদের. This is how we find the flux linkage. N is the number of turns, so that's why. So it is N pi s square into mu 0 N I by 2. I should write 2a. এখানে আমি r লিখেছিলাম. I should write a because the radius I have taken to be a. So this actually gives me N pi mu 0 আগে লিখি, mu 0 N square pi a divided by 2 into I, right? Mu 0 pi n square, mu 0 লিখলাম, pi লিখলাম, n square লিখলাম, a লিখলাম 2. হ্যাঁ, ঠিক আছে. This is the flux phi. Again, you know that if L be the self-inductance of the coil, if capital L be the self-inductance, if capital L be the self-inductance of the coil, if capital L be the self-inductance of the coil, then what actually happens? If capital L be the self-inductance of the coil, so then just now we have learned that the flux linkage is also given by Li. এটাও পড়েছো, flux linkage is given by Li. তাহলে এখান থেকে L টা কত আসে? What is the expression of L? So the expression of L is mu 0 n square pi a divided by 2. So that is the expression what I obtain at this particular moment. So L equals to mu 0 n square pi a divided by 2. So that is the self-inductance of a particular circular coil. So circular coil হলে তার self-inductance এইভাবে বের করা যেতে পারে. Next, let us try to find out the flux linkage of a let us try to find out the flux linkage with a solenoid. একটা সলিনয়েডের flux linkage আমরা এবার বের করার চেষ্টা করি. The flux linkage of a solenoid. How can I find out the flux linkage of a solenoid? Long solenoid. You know the expression of magnetic field of a solenoid from the Biot-Savart's law, from the Ampere circuital law. So Okay, so let us take a solenoid over here. So I put up a heading that self-inductance of a solenoid. Self-inductance of a solenoid. Long solenoid. Self-inductance of a long solenoid. Okay, so you write the introduction same as before. একটা introduction লিখে নিচ্ছি. Let us consider a long solenoid. Let us consider a long solenoid of radius. Let us consider a long solenoid of radius A having small n number of turns per unit, having small n number of turns per unit length and carrying current I. If capital N be the total number of turns, if capital N be the total number of turns, and capital L be the total length, be the length of the solenoid, and capital L be the length of the solenoid, then if capital N be the total number of turns and capital L be the length of the solenoid, then তখন আমরা এটাকে small n টা নিশ্চয়ই এটা লিখতে পারি. For small n I can then write capital N by L. This small n I can definitely write capital N by L. Clear? So let us consider a long solenoid. Okay, I have considered that, and this is the number of turns per unit length. So what is the solenoid, as you know? So this is a non-conducting material, and over this you wound up some wires, some conducting wires. So এরকম একটা non-conducting material, তার মধ্যে তার পেঁচানো আছে. So এই যে পেঁচগুলো আছে, so this is the turns. So how many such turns are there? এটা হচ্ছে একটা turn, this is one turn, then it is the second turn, then it is the third turn, and slowly there are capital N number of turns, and total length of it is capital L. So how many turns are there per unit length? তাহলে প্রতি একক দৈর্ঘ্যে কতগুলো এরকম টার্ন আছে? How many turns are there per unit length? So that is what I first of all find out. Then I write that cross-sectional area of a turn, যেটা আমি ক্যাপিটাল এ দিয়ে লিখছি, সো সেটা আমাদের ক্ষেত্রে নিশ্চয়ই পাই এ স্কয়ার হবে. দ্যাট উইল বি সিম্পলি পাই এ স্কয়ার. লেট ইট বি লাইক দ্যাট. নাও ইউ নো দ্য ম্যাগনেটিক ফিল্ড at any point inside the solenoid, the magnetic field at any point inside the solenoid, the magnetic field at any point inside the solenoid is how much? What is the magnetic field at any point inside the solenoid? The expression is mu 0 Ni, right? That is the expression mu 0 Ni. Is it clear to you? And this small n you may write it to be capital N by L. এটাকে capital N by L করে দাও into current, right? This is the magnetic field. So what is the flux associated with n number of turns? So therefore the flux associated, because ultimately we need to find the flux, because the flux associated with capital N number of turns, the flux associated with capital N number of turns, that should be how much? Flux associated with capital N number of turns, you know the formula of flux. The formula of flux is phi equals to NAB, and then you may write it N A, let it be like that, and B you put over here, that is mu 0 N by 2 into I. So this will give you mu 0 N square, এটা 2 নয়, এটা তো L, this is L, mu 0 N square by L, mu 0 N square by L, capital A into I. So this is the flux linkage with the circuit, right? Now if capital L be the self inductance, if capital L be the self inductance, if capital L be the self inductance of the solenoid, if capital L be the self inductance of the solenoid, comma, তাহলে তখন ফাইটা কত হতো? ইউ নো দ্য এক্সপ্রেশন ফ্লাক্স ফাই ইকুয়ালস টু এল আই ফ্রম আওয়ার লাস্ট থিওরিটিক্যাল ডিসকাশন, লাস্ট যে থিওরি ডিসকাশন করেছি ওখান থেকে তুমি জানো, ফ্রম দেয়ার ইউ নো দ্যাট দ্য ফ্লাক্স ইজ গিভেন বাই এল আই. So you may also write from here that flux is, oh, that flux na. So if you just compare these two equations, so comparing the last two equations, what you can write is that এই দুটো কম্পেয়ার করলে এল এর এক্সপ্রেশনটা কত চলে আসে? The expression of L is mu 0 n square capital A by L. And I definitely hope that this is what you have done in your higher secondary classes. এগুলো তোমরা definitely higher secondary ক্লাসে করেছো. It is just a recapitulation of those ideas, and you will definitely learn something new over here. নতুনও কিছু শেখাবো, আগে এগুলো হয়ে যাক. And this A you may write it to be pi a square if you wish. এটাকে তুমি pi a square লিখতে পারো, ঠিক আছে? So this is all about what you need to know about the self inductances. So self inductance সম্পর্কে যেটা জানার দরকার সেটা তুমি আপাতত জানলে. I have done it for a circular coil and I have done it for a solenoid. Okay, fine. So now in your in your honors category syllabus, honors category syllabus, as you are an honors student, so you should also try to calculate for the case when the solenoid is not long. Okay, for a general solenoid. So এটা আমরা infinitely long solenoid এর জন্য করেছিলাম, and you know for infinitely long solenoid the magnetic field inside is same at all the points due to the symmetry in the figure. That is what you have also find out from the Ampere circuital law. So Ampere circuital law এই জায়গা থেকে আমরা জানি যে ফিগারে সিমেট্রি থাকার জন্য, due to the symmetry in the figure, the magnetic field at any point inside the solenoid is always the same, because you cannot see the two ends of the solenoid. তুমি solenoid এর দুটো এন্ড দেখতে পাও না. So as you cannot see the two ends, so you cannot decide that whether you are towards the left end or you are towards the right end or you are towards the center of the solenoid, because you cannot see the two ends. যেহেতু এন্ডস গুলো দেখতে পাই না, তার মানে আমার কাছে সব পজিশনই আইডেন্টিক্যাল, all the positions are identical to me. To me means to the solenoid, and that is why the magnetic field is same all throughout, and that magnetic field expression is B equals to mu 0 Ni. So that's it. So এই হচ্ছে আমার ম্যাগনেটিক ফিল্ডের এক্সপ্রেশনটা, এটা আমরা শিখেছি. কিন্তু এখন এবার কি করতে হবে? হোয়াট ইউ শুড ডু আফটার দিস? আমরা এখন কনসিডার করব if the solenoid is not too long. If the solenoid is not long, মানে জেনারেল সলিনয়েডের যে এক্সপ্রেশনটা আছে, সো দেন ইউ উইল ইউজ দ্য জেনারেল এক্সপ্রেশন ফর সলিনয়েড. লেট আস রিকল হাউ ডিড উই কনসিডার ইট ইন আওয়ার প্রিভিয়াস ক্লাসেস. আমরা মনে করে নিই আমরা আগের ক্লাসে কি করে ধরেছিলাম সলিনয়েডটা, এবং সেভাবেই আমি একটা তোমাকে ট্রিটমেন্ট দেখাবো, বিকজ অ্যাজ ইউ আর দ্য অনার্স স্টুডেন্ট ইউ মাস্ট বি অ্যাকাস্টমড উইথ ইট. অনার্সের ছাত্রদের এটা কিন্তু অ্যাকাস্টমড হওয়াটা দরকার, সেই জন্য আমি এটা এখানটাতে দেখিয়ে দিচ্ছি. দেখো ভালো করে. সো দ্য ওয়ে উই কনসিডার দ্য সলিনয়েড ইজ সামথিং লাইক দিস. It is the axis of the solenoid, and then you consider the turns over here. Difficult. Okay, let it be like this. More or less I have tried to draw. মোটামুটি চেষ্টা করেছি. And then over here I consider, you see, I consider a small element dx over here at a distance x from one end. At a distance x from one end of the solenoid, I consider a small element dx. এখানে একটা dx element consider করলাম at a distance x from one end. And you know that how do I consider the angles over here? এখানে আমরা অ্যাঙ্গেল গুলো কি করে ধরি তুমি জানো. This is a point capital P, suppose এটা যদি একটা capital P point হয়. So from capital P I actually join these two ends. Capital P থেকে আমরা এই দুটো এন্ডকে জয়েন করে দিই. this angle we consider it to be theta 1, and this angle, I have said that both the angles are considered in the same direction, that is the clockwise. In your book it may be different, তোমাদের বইয়ে অন্যরকম থাকতেই পারে, don't get confused with that. And L be the length of the solenoid. So L length was capital L. Capital L is the length of the solenoid. Finite length, not too long. Right. আচ্ছা ঠিক আছে। এটা করার জন্য আমরা যেটা করব সেটা হচ্ছে, whatever I will consider is that, so consider a small element, consider a small element dx, consider a small element dx at a distance, consider a small element dx at a distance x as in the figure. The magnetic field at the region of this element, যে জায়গাটাতে আমি এলিমেন্টটা নিচ্ছি, the magnetic field at the region of this element will be how much? What is the magnetic field at the region of this element? এই জায়গায় ম্যাগনেটিক ফিল্ডটা কত হবে? What will be the magnetic field? So the magnetic field at this particular region will be B equals to, এখানে ম্যাগনেটিক ফিল্ডটা কত হবে? The magnetic field will be B equals to mu 0 Ni by 2, right? The magnetic field at this position, you know the expression, please look at your previous classes of Biot-Savart's law. Biot-Savart's law এর ক্লাস দেখো, ওখানে পেয়ে যাবে, you will get it in the class of Biot-Savart's law. Mu 0 Ni by 2 cos of theta 1 minus cos of theta 2. got it? পেয়ে গেছো নিশ্চয়ই। This radius is A. আচ্ছা এখানে ভ্যালুগুলো পুট করো দেখি একটু। mu 0 Ni by 2, mu 0 Ni by 2 n I write n by L now only, আমি এটাকে n by L করে দিচ্ছি। cos theta 1, এখানে cos theta 1 কত হবে? what is the cos theta 1? base by hypotenuse x by root over of a square plus x square, base by hypotenuse plus তো নয় minus cos theta 2, cos theta 2 মানে এখানেতে actually cos theta 2 I cannot find, I will find actually cos of pi minus theta 2, right? আমি actually cos of pi minus theta 2 মানে এইটা বের করছি, I will find the cos of this angle, cos of pi minus theta 2, okay? And cos of pi minus theta 2 is minus cos theta 2, so whatever I am trying to find is the value of minus cos theta 2. আমি পুরোটার ভ্যালুটা বের করছি, try to understand. I am trying to find the value of this one, and what is this? This is pi minus theta, but cosine of pi minus theta is nothing but minus cos theta. So actually আমি যার ভ্যালু বের করছি, I am trying to find the value of minus cos theta. So togetherly I find the value of minus cos theta, which will be found from the right end. এই সাইড থেকে বেরিয়ে আসবে এটা, তাহলে এই সাইড থেকে করলে এটা চলে আসবে। again হচ্ছে base by hypotenuse, so this time the base is L minus x, so this time the base is L minus x divided by hypotenuse অতিভুজ, that is a square plus L minus x whole square, that is the expression this time. So এটা এইবারের এক্সপ্রেশন, এটা ম্যাগনেটিক ফিল্ডের এক্সপ্রেশন আসলো। এইবারে the amount of flux linked with the turns within dx, the amount of flux within the turns in dx, আচ্ছা এইটুকু জায়গায় কতটা ফ্লাক্স থাকছে? what is the flux within this region? What is the flux in this region? Let us try to find out what is the flux. Let it be defined. You know that the flux linked, how many number of turns are there? ওখানে কতগুলো টার্নস আছে বলো তো? number of turns over there is n by L into dx, right? Because n by L is the number of turns per unit length, and in the dx length how many turns are there? You have done it in the classes of Biot-Savart's law. So number of turns per unit length is n by L, and within this dx how many turns? এখানে কতগুলো টার্নস আছে? এতগুলো টার্নস আছে। formula for flux is NAB, the formula for flux is NAB. So n is done. Now area, what is the area over here? What is the area? So let A be the area of cross section, which is nothing but pi a square, and the magnetic field B is how much? So B is this one only. এখানে দুটো জিনিস আমরা অ্যাজিউম করেছি, A হচ্ছে, A is the cross sectional area, A is the cross sectional area of a turn, and capital B, you see I have made an assumption over here also, এখানেও আমরা একটা assumption করেছি, and the assumption is that capital B, right, is assumed to be constant, is assumed to be uniform, is assumed to be uniform over the cross section of a term, is assumed to be uniform over the cross section, is assumed to be uniform over the cross section of a turn, is assumed to be uniform over the cross section of a turn, right? So B is assumed to be uniform over the cross section of a turn, over the cross section of a turn, right? তার মানে অ্যাকচুয়ালি তুমি যে বি এর এক্সপ্রেশনটা ইউজ করেছো, দ্য এক্সপ্রেশন অফ বি দ্যাট ইউ হ্যাভ ফাউন্ড, ইউ রিমেম্বার দ্যাট দিস বি ইজ অ্যাকচুয়ালি দ্য বি অন দ্য অ্যাক্সিস অফ দ্য সলিনয়েড। এই যে বিটা আমরা বের করি, এই বিটা কোথাকার বি? দিস ইজ দ্য বি অন দ্য অ্যাক্সিস অফ দ্য সলিনয়েড, বাট I consider the B to be same over this entire cross section. এখানে গোটা cross sectionটাতে আমি মনে করছি the magnetic fieldটা আমি এটা ইউজ করব। So this much assumption is used. So this much have to be used in order to get some idea. কিছু আইডিয়া পাওয়ার জন্য এইটুকু তোমাকে this much sacrifice has to be done, because we have calculated the magnetic field from Biot-Savart's law only on the axis but not on any other points. So this much sacrifice is to be done in this particular calculation. এই sacrifice তোমায় করতেই হবে. So d phi is given by this expression, right? Okay, next. Put the value of B over here. এখানে B এর যে ভ্যালু আছে সেটা বসিয়ে দাও, তারপরে পুরোটা ইন্টিগ্রেট করতে হবে। So I should arrange it in proper way. So you see that if I put the value of B, so then it is mu 0 I by 2, leave it, n by L whole square, leave it, তাই তো? mu 0 I by 2, n by L দুবার আছে, so এটা whole square হবে, leave it, then there is a capital A, fine, and then you write the terms within the third bracket with a dx, x divided by root of a square plus x square plus L minus x divided by root of a square plus L minus x whole square, this one totally multiplied to dx. এই টোটালটা dx দিয়ে মাল্টিপ্লাই করা। তাহলে what is the total flux linked with the solenoid? Total flux linked with the solenoid, total flux linked with the solenoid. So last time this confusion didn't arise for a long solenoid. Long solenoid এগুলো কেন arise করেনি? Because for a long solenoid over the entire solenoid the expression was same, and that expression was how much? It is mu 0 ni. So whatever be the point, the magnetic field is same at all the points. So that's why what did you do to get the total flux? Total flux টা করার জন্য কি করতে হয়েছিল? You just multiply NAB. The magnetic field is same all throughout. That is NAB, right? But this time you cannot do it because the magnetic field is different at different point. So এক একটা পয়েন্টে magnetic field আলাদা আছে. So what do? I consider a small cross section and find the flux linkage over there, because the flux linkage over this cross section and the flux linkage over this cross section will be different. এখানকার flux linkage আর এখানকার flux linkage আলাদা হবে। কেন? Because এখানে magnetic field গুলো আলাদা, the magnetic fields are different. So you cannot multiply the entire thing with this B. পুরোটাকে B দিয়ে মাল্টিপ্লাই করা যাবে না। The entire you cannot multiply with B, right? Because B's are not now constant. Magnetic field is not a constant, but you have to find the magnetic field at a particular point. At a particular point a magnetic field বের করো, and then magnetic field, from that magnetic field you calculate the flux, সেই magnetic field থেকে flux বের করো, and then you integrate to get the total flux, তারপরে integrate করে total flux বের করো। So this is the idea over here, this is the basic idea over here, fine. Total flux linked with the solenoid, total কত flux link হতে পারে এই সলিনয়েডের সঙ্গে? So that is phi equals to integration of d phi. Let us perform this integration very quickly because this is just a mathematics. Integration of x root over of a square plus x square The limit of integration is from 0 to L, the total length of the solenoid. Okay. One thing you should do over here very carefully. এখানে একটু কায়দা আছে, হ্যাঁ, এটা ভালো করে খেয়াল করো এখানটাতে। This one is z dz divided by z. Integration limit is a to root over of a square plus l square. This one is minus of root over of a square plus l square to a. This is y dy by y. Now the question is, where from do I get all this? এই এত কথা আমি কোথা থেকে পেলাম দেখিয়ে দিচ্ছি কোথা থেকে পেলাম। where from do I get it? So I use a blue ink. So এখানটাতে আমি যেটা করেছিলাম সেটা হচ্ছে let a square plus x square, a square plus x square, I have taken it to be z square. So I understand that x dx will be z dz. So that is what I have substituted for the first integral. প্রথম ইন্টিগ্রালটাতে তাই করেছি। And if you go through the limits, you will automatically understand. Limits টাও দেখে নাও এর। X, and this is for z. If the limit is 0, so then z is a, and if x equals to l, then it is, you understand, it is a square plus l square. Clear? এটা হচ্ছে একটা পার্ট। আর একটা হচ্ছে and the second part I assume a square plus l minus x whole square. This one I assume it to be y square. So from here I get minus 2 times of, not 2 times, minus minus তো থাকবেই, minus of l minus x dx, minus of l minus x dx is equals to y dy. তাই তো, minus of l minus x dx. So that's why l minus x dx I put a minus over here. এখানে মাইনাসটা এসছে। And here also if you go for the limits like this, এখানেও যদি তুমি লিমিটস গুলো দেখে নাও তাহলে এখানেও তুমি দেখতে পাবে, here also you will find that this is for x and this is for y. x is 0 to l, sorry, x is 0 to l. So এখানে যদি তুমি 0 পুট করো x এর জায়গায়, so if we put x equals to 0, right, x equals to 0 পুট করলে এটা আসছে root over of a square plus l square, and if you put it to be l, then it comes out to be a. So that's why the limit is of this form. Right, clear আছে একদম? So this is what I have done. So এটাই আমি এখানটাতে করলাম। I come back to my reading to get phi. So এটাকে কমপ্লিট করলে phi এর এক্সপ্রেশনটা যেটা আসবে সেটা হচ্ছে mu 0 I by 2 into capital A. Within the brackets I will have the first one gives me root over of a square plus l square minus a, and the second one gives me a minus root over of a square plus l square. So I understand that a gets cancelled and I have that a square root over of a square plus l square. Oh no, nothing gets cancelled here. Minus minus plus, and oh, nothing gets cancelled, so it is just 2 times. So just এখান থেকে এটা 2 times হয়ে যাচ্ছে, this becomes 2 times and 2 gets cancelled. So I have mu 0 n square capital A pi l square, 2 gets cancelled, root over of a square plus l square minus a multiplied to I. Right? Comparing to, you may compare this relation comparing to phi equals to Li. L is the self-inductance of solenoid. L is the self-inductance of solenoid. Comparing to this, we have L equals to, এখানে তুমি L এর এক্সপ্রেশনটা পেয়ে যাচ্ছ, L equals to mu 0 n square by L square capital A, mu 0 n square by L square capital A, and then I have root of a square plus L square minus a square plus L square minus. So that's the final. Oh, now you see that 2L are now disturbing. 2 L to আমাকে disturb করছে. So I have taken it to be capital L, but finally I understand that capital L is going to create a problem. তাহলে এই যে length of the solenoid, you make all of them to be small l. এই solenoid এর length গুলোকে সব small l করে নাও, কিছু করার নেই. At the very end I find this difficulty, but this is what you can understand or clarify yourself. এটা তোমরা নিজেরা করে নিতে পারো. তো সলিনয়েডের লেংথ গুলোকে সব স্মল এল করে নাও. ইউ টেক দ্য লেংথ অফ দ্য সলিনয়েড টু বি স্মল এল. আইদার এটা করতে পারো, আর নয়তো এটা যখন ক্যাপিটাল এল আছে থাক, তো আর কিছু করার নেই. সো অ্যাজ ইট ইজ ক্যাপিটাল এল, সো নাথিং টু ডু ওভার হিয়ার. জাস্ট এটাকে তাহলে এল ড্যাশ করে নাও. ইউ টেক দিস টু বি এল ড্যাশ. The self inductance you just take it to be L dash, but please make a correction at the time of exam. পরীক্ষার সময় এইভাবে করো না. At the time of exam you take small l to be the length and capital L to be the self inductance. Here I have done it mistakenly, so just please check it yourself. So এটা একটু নিজেরা চেক করে কারেকশনটা করে নিও. এটা ঠিক আছে. আর যদি খুব লং সলিনয়েড হয়, if it is a long solenoid, if A by L is less 1, you know that this is the condition of a long solenoid. এটা হচ্ছে long solenoid এর condition, you know this one. So therefore under that condition you may write L dash equals to mu 0 n square by L square capital A, and here you may take common. You just take this L common. L টাকে যদি common নিয়ে নাও, here I have a L and I have 1 plus a square by L square to the power of half minus A. If I go for a binomial over here, if I go for a binomial expansion, mu 0 n square by L square into A into L, I go for a binomial expansion. I just remove the square because it gets cancelled. এখানে binomial expansion করলে আমার কাছে থাকবে হচ্ছে 1 plus a square by 2L square. Is it so? Not needed. এইভাবে করার দরকারই নেই. No need to do this way. They have suggested an alternative way. ওইটা হচ্ছে mu 0 n square by L square into capital A. You see that A is less L. The condition is A is less L or L is very large. Long solenoid মানে L টা খুব বড়. So with respect to this L, you may neglect this A. এই A গুলোকে বাদ দিয়ে দিতে পারি আমি. তাহলে এখান থেকে শুধু L থাকবে. I have only the L. I neglect this A's from here. So this will result in L dash is equals to mu 0 n square capital A by L. So that's the expression, and you match up with the earlier expression mu 0 n square by L. আগেরটার সাথে ম্যাচ করো, দেখো তাই আসবে. You see over here mu 0 n square by L into capital A. Is it clear? So it well matches with our expression. So I hope that you have understood the situation. So নিশ্চয়ই বুঝতে পেরেছো সিচুয়েশনটাতে আমরা কি করতে চাইছি, right? So here the discussion on self inductance is over. Self inductance এর discussion এখানেই শেষ হলো. If you go through your book, the book that I have recommended, the book of B. Ghosh, the electricity book, here you will see that there are other calculations related to this self inductance. Self inductance এর দেখবে আরো ক্যালকুলেশন এখানে আছে. I have done the solenoid one for you because this is the most important one. If time have permitted, then I would have shown you one or two more, that is for transmission line, for a toroidal coil. I would have shown you definitely as I used to do, but due to the lack of time I couldn't go through those. আমি সেগুলো এখন দেখাতে পাচ্ছি না. So you are requested to go through those yourself. So তোমরা সেগুলো কিন্তু নিজেরা একটুখানি করে নেবে. Just nurture your book. So একটু বইটাকে একটু দেখে নেবে. So বইয়ের মধ্যে করে দেওয়া আছে. Whatever was my intention was to make you understand the methodology of the calculation. যে কি মেথডে ক্যালকুলেশন হয়. Now once the methodology is shown to you, I believe that everybody of you can do them yourself if you just look at the book, because the task of the instructor is to make you know the methodologies. আমাদের কাজ হচ্ছে মূলত তোমাকে মেথডস গুলো জানিয়ে দেওয়া যে কিভাবে করতে হয়. What do you have to study and how do you have to study? So I have shown you the methodology. I have explained you the physics of self inductance. Self inductance এর physics তোমাকে বলে দিয়েছি, that how to study self inductance, that has been discussed with you, and now it's your task to go through a few examples. So কয়েকটা example, and those are solved in your book. You just go through the topic of self inductance. The first one is the solenoid. You will see that this is the one that I have done, and there are others in that particular book, so you are requested to find some time and go through them. Okay, although those are less important for your examination, because whatever I am trying to discuss, keeping in mind the point of view of your examination, but still it's better for you to go through them. So একবার দেখে নেওয়া কিন্তু ভালো, তাহলে তুমি একটু ভালো করে শিখতে পারবে, you will learn the things carefully. Okay, the next discussion is on mutual induction. So we have already discussed about self induction. You have understood the concept of self induction, and now the concept is of mutual induction. So mutual means the effect of one on another. Ektar effect araktar upore kotota. The effect of one on another, that is what is mutual inductance. Now let us try to understand the concepts of mutual inductance. So in mutual inductance we will consider at the very beginning two coils. Amra ekhane duto coil dhore nebo. We will consider two coils over here. Suppose this is a coil and this is another coil. Not necessarily they are parallel, so I will just try to draw them like this. Not necessarily the coils are parallel, they are oriented some way. Suppose a current is flowing through this particular coil A. This coil I name it coil A, and this one suppose I call it a coil B. Not necessarily they are circular, but they must be closed. Circular hote hobe emon kono byapar nei, kintu jeno closed hoy. Those are closed coils. Now suppose we have two closed loops. Suppose we have two closed loops, or closed loops capital A and B, placed close to each other, right? First point, if a current suppose I1, if a current I1 flows in A, if a current I1 flows in capital A, comma, then it will produce some magnetic field, at the position, of capital B, and hence some flux will get linked, with capital B. This is what I learned, right? If I1, I write it in this way, আমি এভাবে লিখলাম, হ্যাঁ, I1 মানে এই I1 টা, this I1 only. If I1 varies with time, then what will happen, comma, then there will be a rate of change, of flux, in B. So then there will be a rate of change of flux in B, which will give rise to some induced EMF, in capital B, and this phenomena is known as mutual induction. That is the effect of A on B. Now try to understand, এবার বোঝার চেষ্টা করো আমি কি বললাম. Try to understand what did I say. I say that current is flowing through A, there is no current in B, but due to this A there will be some magnetic field through B. দেখো এই এখান দিয়ে কারেন্ট গেলে এটা দিয়ে কি হবে, এই জায়গাতে কিছু ম্যাগনেটিক ফিল্ড তৈরি হবে. there should be some magnetic field in this particular region. Throughout the region there will be some magnetic field because of the current in A. Now because of this current in A, some flux is linked with B. এই যে B এর সাথে দেখো flux linkage আছে, there is some flux linkage with B. Now suppose that the current changes in A. A তে যে কারেন্টটা আছে, the current in A changes with time. So this current change with time. So what will happen? The flux linked with B, that flux will also change with time, and hence there will be some d phi dt, and you know that d phi dt is equals to E. So that is how some induced EMF will be produced in this particular coil. সো এইভাবে এই কয়েলে একটা ইনডিউসড ইএমএফ হবে, and definitely the direction of the current in coil B will be opposite to that of A. Definitely the current in coil A will be opposite to that of A, because you know from your higher secondary classes only that for a current carrying conductors, if the current are in the same direction, they will attract each other, but if the current are in opposite direction, so they will repel each other, and repulsion is very essential over here due to the Lenz's law, due to the Lenz law of electromagnetism. So that is why, so Lenz law, you know, it will oppose its own cause. So that is why if the current is over here anti-clockwise, so in this one the current must be clockwise. So that's why you decide the current in the two conductors. Okay, fine. এবার কথাটা দেখে নাও, we have two loops A and B. If a current I1 flows through A, then it will produce some magnetic field at the position of B, right? So there will be some flux linked with B, এখানে flux linkage থাকবে, there will be some flux linked with B, and if I1 varies with time, here it is I1, okay, এটা কিন্তু I1, if I1 varies with time, then there will be a rate of change of, let me correct it over here, এখানে ঠিক করে লিখছি আমি এটা, what should I do? I just remove it, put some, if I1 varies with time, then there will be a rate of change of flux. So there is some flux. If the current varies, then the magnetic field will vary, and hence the flux in B will vary. And wherever there is a change in flux, you know that wherever there is a change in flux, যখনই flux change করবে সঙ্গে সঙ্গে কি হবে? Where will be there is a change of flux, there will be a induced EMF. As soon there is a change in flux, there will be a induced EMF in the circuit. Circuit একটা induced EMF থাকবে. There will be a induced EMF in B. And this effect is known as mutual induction. That means the effect of A on B. A এর effect B এর উপরে. The effect of A on B. Is it clear to you? Similarly, you can do the same if the current in coil B is varied. Right? সেখানটাতে সেটাও আমরা লিখে রাখছি ব্র্যাকেটে। Similarly, there will be induced EMF in coil A. Similarly, there will be induced EMF in coil A if the current in coil B is varied. If the current in coil B is varied. Okay, that can be also done. That's the vice versa process. So if there is a current over here and there is no current, so by varying the current in B, you can induce some EMF in A. That can also be done. Okay, now let us come to the mathematics of it. So এবার আমরা mathematics টা discuss করি. The flux through coil B, due to the current in coil A, the flux in coil B due to the current in coil A, that will be how much? The flux through coil B due to the current in coil A, that is phi 2. Okay, the flux through coil B মানে second coil, due to the current in coil 1, that will be phi is proportional to I. So in the classes of self inductance, you have come to know that flux is proportional to current, right? But there the 1-2 was not required because self inductance means there was a single coil only. So this property you know from your classes of self inductance. Self inductance এর property থেকেই তুমি জানো that this flux phi is always proportional to this I. এটা হচ্ছে I এর সাথে proportional হবে. This will be proportional to the current I in the circuit. So now over here it is the effect of the second, effect on the second due to the first. So first coil এর current কত? What is the current in the first coil? It is I1. And what is the flux through the second coil? It is phi 2. Now in order to remove this proportionality, you need a constant, and that constant I call M21. So this constant I call it M21. এটাকে আমি M21 বলছি। Is it clear? আচ্ছা, এটা একটা গেল। Similarly, the flux through coil B due to coil A, the flux through coil A due to coil B, তখন কি হবে? The flux through coil A due to coil B, that will be how much? That one will be phi 1, the first coil is proportional to I2, the current on second coil. That one will be phi 1 is equals to M12, effect of 1 due to 2, effect on 1 due to 2, that is M12 I2. Now here we call where M12 comma M21 are the mutual inductances of the loop. These are called the mutual inductances of the loop. And it can be shown, which we will also show. It is in our course, very important question for your exam. And it can be shown that M12 is equals to M21. It can be shown, okay? It can be shown that M12 is equals to M21, right? Means the mutual inductance of 2 due to 1 and the mutual inductance of 1 due to 2, they two are equal, right? Okay, what about the induced EMFs? You may write over here. The induced EMF in coil 2 due to coil 1. The induced EMF in coil 1 by coil A, due to coil 2 means coil B. E is how much you know. What is the formula for E? E you know, it is d phi dt. Induced EMF in coil A to aage korini. First of all, I was doing it for coil B. Effect of induced EMF in coil B due to coil A. It was, if I go for a mod value, induced EMF in coil B due to coil A. Coil B, that means it should be d phi 2 dt. I am taking the mod value, okay? I am not using that negative sign due to the Lenge's law. Now this is simply M21. It is simply asche M21 di1 dt. It is M21 di1 dt. Got it? আর লাস্টের কাজটা একই রকম ভাবে, the induced EMF in coil A due to coil B, that should be how much? এটা কত হবে? E equals to, again if I write mod coil A, the induced EMF in coil A, that should be, it should be d phi 1 dt. So that is M12 di2 dt. So these are the two expressions that you get over here for the EMFs. This is how we get to know about the mutual inductance. So এইভাবে আমরা mutual inductance সম্পর্কে জানি. This is how we come to know about the mutual inductance, and this is how we define M21 and M12. And it is also possible to prove that M12 and M21 are equal to each other. একজন আরেকজনের equal. Let us now go for the calculation of mutual inductance for simple geometries. So দু একটা geometry mutual inductance আমরা একটু বের করি. Let us try to find the mutual inductance of a few geometries. So mutual inductance of two solenoids. 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 দুটো সলিনয়েড আমাদের কাছে আছে. I have two solenoids. I have to find the mutual inductance of one due to the other. Let us draw the solenoids over here. আমরা solenoids গুলো draw করে নিচ্ছি. This is the first solenoid. And this one is the second over the first, and we will consider long solenoids. আমরা definitely long solenoid এর expression use করব. So these are the turns for the primary solenoid. I call one of them to be the primary. The blue one is called the primary and the red one will be called the secondary solenoid. Blue টাকে আমরা primary solenoid বলছি, red টা হচ্ছে আমাদের secondary solenoid. Red is the secondary solenoid. Okay, so I have two solenoids over here. These are the free ends available for connections. আর এখানে these are the free ends available for connections. This one I call PP for primary, and this ends I call SS for secondary, primary and secondary. So let us write it. So let us consider a long solenoid So one of them is long. Let us consider a long solenoid, capital P, over which a very short solenoid, let us consider a long solenoid over which a very short solenoid, capital S, is wound. If capital I be the current, flowing through the primary, if capital I be the current flowing through the primary, and small n is the number of turns, and small n is the number of turns per unit length, then the magnetic field at any point inside the solenoid, comma, then the magnetic field at any point inside the solenoid, is, okay, as it is a long solenoid, so the magnetic field at any point inside will be same, and that is mu 0 Ni. The magnetic field at any point inside is mu 0 Ni, right? And this one I can write it to be, এটাকে আবার আমি লিখতে পারি mu 0 N1 by L into I. যেখানে আমি কি লিখছি, N1 is the total number of turns in capital P, and small l is the length of capital P. Total number of turns of capital P, and it is the length of capital P. So that's why small n I can write N1 by L. Safely I can write it. How did I write the current? Oh, current I write by capital I. So I should write capital I over here. Okay, that's the magnetic field at any point inside. Can এটা হলো because it is a long solenoid. So the magnetic field is same at all points, and I take it like this. Now suppose I take it in this way, N2. This is the total number of turns. N2 টা কি? N2 is the total number of turns of capital S, and capital A is the cross-sectional area of each turn, of S, right? Here also you have to make that assumption, assuming capital B to be uniform, over a cross section, assuming capital B to be uniform over a cross section, the flux linked with the secondary, try to understand the method of calculation without losing yourself in the mathematics. Mathematics এর মধ্যে হারিয়ে যেও না. Don't get lost in the mathematics. Try to understand the methodology of the calculation. Mathematics you can do anywhere, anytime. So the flux linked with the secondary, that will be phi 2 is equals to N2 into A into B. That means that it is N2 into A, and then it is mu 0 N1 by L into I simply. Or you may arrange it properly, ভালো করে গুছিয়ে লিখলে mu 0 N1 into capital A divided by L, mu 0 N1 into capital L into I. That is the flux. This is phi 2, right? এইবারে if capital M be the mutual inductance, of the system, then you may write phi 2 is equals to capital M into I. তাই তো হবে, the flux is capital M into I if capital M is the mutual inductance. So comparing you may say, so এটা যদি compare করি আমি, comparing you may safely say that comparing capital M is equals to, so just comparing you may write capital M is equals to how much? Capital M is equals to how much? If you just compare, then it comes out to be mu 0 n1 into capital A divided by L. That's the expression. Now one thing I just made a small mistake over here, একটা ছোট mistake আমার হয়েছে, সেটা হচ্ছে here capital A is the cross section of the cross sectional area of each turn. Cross sectional area of each turn, you write it like this, cross sectional area of each turn over here. এখানে s লেখার দরকার নেই. At the end you write, একদম শেষে গিয়ে তুমি লেখো একটা স্টার দিয়ে, at the end you may write it, A is the area, A is the area of each turn, A is the area of each turn of the primary, A is the area of each turn of the primary. Now this appears confusing to you, এটা তোমার কাছে confusing মনে হচ্ছে, that as you are finding the flux linked with the secondary, তুমি the secondary flux বের করছো, you are finding the flux linked with the secondary, so you must consider the area of the secondary. তাহলে তোমার তো secondary এরিয়াটা নিতে হবে, you have to consider the loop of the secondary. Why? Because you are considering the secondary, the flux linked with the secondary. But the interesting thing over here is that, interesting ব্যাপারটা হচ্ছে যে you know that the magnetic field at any point outside the solenoid is 0. As soon as you are using this expression of B in the secondary, যখনই তুমি এই এক্সপ্রেশনটা ইউজ করছো B এর, দেখো আজকে তো প্রাইমারি সলিনয়েডটা আছে, you have a primary solenoid, the magnetic field at any point inside the primary solenoid is how much? It is B, right? And this is B only within this primary solenoid, এই প্রাইমারিটার ভেতরেই শুধু B, because you know that outside the solenoid the magnetic field is 0. That has been done from the Ampere circuital law. Outside the solenoid the magnetic field is always always 0. Outside the solenoid the magnetic field is always 0. তার মানে তুমি যে ম্যাগনেটিক ফিল্ডটা এখানে ইউজ করেছো, the magnetic field that you have used over here is which magnetic field? The magnetic field of the primary. And definitely in this region B is 0. এই রিজন বা এই রিজনে তো কি হবে? B টা তো 0ই হবে. In this particular region B is definitely 0, right? B টা তো 0 হবে. So there is no effect of this region of the solenoid. Solenoid এর এই রিজনটা কোনো এফেক্টই আসবে না. This region of the solenoid is of no effect. This region of the solenoid is of no effect. So that's why when you are using the expression to be B, although it should be the area of the turn of S, যদিও এটা S এর এরিয়াটাই হবে, this should be the area of the turns present within the secondary solenoid, this should be the area of the turns of the secondary solenoid, yet we are using the area of the primary solenoid because the B, the magnetic field B is only enclosed within the blue line. The magnetic field B that is you are using, that is enclosed only by the blue line. এই যে B টা যেটা ইউজ করছো সেটা শুধুমাত্র blue line দিয়ে enclosed. So that is why you must consider the area of the blue line only. So that is why I write at the very end that A is the area of each turn of the primary. This is what you should understand very, very clearly, that why you are using the area. Because if you are going to solve some numerical examples, so then you may be in some trouble. So numerical example করতে গেলে তুমি trouble এ পড়ে যেতে পারো. You may be in trouble while solving numerical examples. So that's why we just provide you the ideas. Because you know that area is nothing but pi into radius square, but what radius is to be used? So to put you in a trouble, so they may provide you both the radius, right? So দুটো radius দিয়ে দিল, তখন তুমি কিন্তু trouble এ পড়ে যাবে, then you will be in trouble, right? So that is why I just make you careful at the very beginning. আগের থেকেই তোমাকে আমি careful করে দিলাম. Okay, right, fantastic. Okay, next. And next I will go for the last calculation of the day. May not be the last, so that depends upon how much do we proceed. So কতদূর করতে পারছি তার উপর, may not be the last calculation. So let us first of all go through it. So mutual inductance for two parallel circular coils. Mutual inductance for two parallel circular coils. one thing in the last treatment I have just forgot to mention. So একটা জিনিস বলতে ভুলে গেছি, সেটা হচ্ছে you see that the magnetic field B that I have found, that B is only on the axis of the solenoid. আমরা যে B এর এক্সপ্রেশনটা করছি সেটা কিন্তু শুধুমাত্র অ্যাক্সিসে। The expression of B is only for the axial points, but I take the expression to be same throughout any cross section. এই গোটা ক্রস সেকশনে কিন্তু আমরা সেম নিয়েছি। I have taken the expression to be same over the entire turn. এই পুরো যে টার্নটা আছে, over the entire turn I take it to be B. Although B is the expression only at this point only, at the top and bottom point it is not the same. Yet I have taken so, but still আমরা এটা নিয়েছি। So this is a sacrifice that we have made to ultimately get some calculation with reduced labor. Because if I want to find the magnetic field at each and every point, so that will be a very very non-trivial task and it is not done anywhere. So people usually don't do it. So কোনো মানুষই সেটা করে না, so people don't do it. So we also have taken that advantage, and this advantage can be taken if the cross section is very small, that is the radius is very small. And for long solenoid it is definitely the case, because for long solenoid you know A is less than A. The radius is very small for a long solenoid, so this assumption can be made for a long solenoid. So এই assumptionটা আমরা করতেই পারি that throughout the cross section I have taken the magnetic field to be the same. I have written it somewhere. Assuming B to be uniform over a cross section, the flux linked with the secondary. Over the entire cross section A, I have taken the magnetic field to be same magnetic field আমরা নিয়েছি. So this is the assumption that we have made to get some good result, because you see that the calculation is not too simple even after taking this much, even after making this sacrifice. এই স্যাক্রিফাইসটা করার পরেও কিন্তু খুব একটা সহজ ক্যালকুলেশন না, অনেকটা কাজই আছে। তো সেই জন্য আমরা এইটুকু অ্যাডভান্টেজ নিলাম। So we have taken this much of advantages over here, right? So now let us go through another calculation that is for two circular coils as per your syllabus. So আমরা দুটো সার্কুলার কয়েল এখানে কনসিডার করছি। I consider two circular coils over here. These are the two circular coils that I consider. They are coaxial. Center of this one is O1. Center of this one is O2. This one I take it to be of radius A, and this one I take it to be of radius B. একটা radius A নিয়েছি, একটা radius B নিয়েছি। Here the current flowing is I. This coil I name it as C1 and this coil I name it as C2. এই হচ্ছে দুটো coil, and the current flowing through one of them is I, and X is the intermediate distance between these two particular coils, right? Let us write an introduction first about it. That let us consider two parallel coaxial coils. Let us consider two parallel coaxial circular coaxial. Two parallel circular coaxial coils C1 and C2. I write it in this way: C1 and C2 of radii A and B respectively. First point, separated by distance x. I be the current flowing through C1. I be the current flowing through C1 which induces an EMF bracket we write current, which induces an EMF in C2. I be the current flowing through C1 which induces an EMF in C2. Now here we start the calculation. First of all, I need to find the magnetic field due to this current. এই কারেন্টের জন্য magnetic field টা কত হবে at the position of the coil C2. So first of all, write that the magnetic field the magnetic field due to C1, the magnetic field due to C1 at the position of C2, the magnetic field due to C1 at the position of C2 will be how much? The magnetic field due to C1 due to this coil at the position of C2 will be how much? So the expression is known to us from our previous classes. It is mu 0 Ni square divided by 2 times of a square plus x square to the power of 3 by 2. Right? This is the expression where n is the number of turns of C1. N is the number of turns in C1. N is the number of turns in C1. Okay, mu 0 Ni square divided by 2 times of a square plus x square to the power of 3 by 2. Achha. So this is the magnetic field at the position of the coil C2. Actually, this is the magnetic field only at this point, at a distance x from the center of the coil. You remember the treatment I have done from Biot-Savart's law, the magnetic field at the point P. So basically the expression that I have written now is the magnetic field at this particular point only, not the entire cross section, puro cross section is not. But yet I will take the magnetic field over the entire cross section to be this B. So this much sacrifice as we are making, we have to make this sacrifice. We assume that this magnetic field is uniform throughout the cross section, throughout the cross section of C2, throughout the cross section of C2. So this much sacrifice we have to make, that the magnetic field is same. Actually this is the expression at the center of this C2, but I assume that the magnetic field to be same throughout this C2. So we assume that this magnetic field, is uniform throughout the cross section of C2. Right. Now let capital A equals to pi b square area of C2, capital N2 number of turns of C2. So therefore the flux linked with C2 will be how much? Therefore flux linked with C2. What is the flux linked with C2 due to the current in C1? The flux linked with C2, that will be phi 2, will be N2AB. As fine expression ache N2AB. Let me put the expressions over here. So I put N2. For A I put pi b square, and for B I put mu 0 N1 Is square divided by 2 times of a square plus x square to the power of 3 by 2. Okay. Next I can write this to be mu 0 N1 N2, mu 0 N1 N2 pi times of a square b square divided by 2 times of a square plus x square to the power of 3 by 2 into I. Right? So this is the flux linked with C2. This is the flux linked with C2 due to the current in C1. Now you may write, if capital M be the mutual inductance of the system, if capital M be the mutual inductance of the system. Why do I call system? Because previously I have said that mutual inductance is such a parameter which is same for either of the coils. That is M12 is equals to M21. If capital M be the mutual inductance of the coil, if capital M be the mutual inductance of the coil now of the system, if capital M is the mutual inductance of the system, তখন আমি লিখতেই পারি that phi 2 is equals to capital M into I. I can write it. If capital M be the mutual inductance of the system, then phi 2 is equals to M into I. So from here I can write that what is the value of M then? তাহলে এখান থেকে M এর ভ্যালু কত? So the value of M comes out to be mu 0 N1 N2. It comes out to be mu 0 N1 N2 pi times of a square b square divided by 2 times of a square plus x square to the power of 3 by 2. So that is how I get the mutual inductance of this particular coil. Right? Mutual inductance of the system. এখান থেকে একটা স্পেশাল কেস আমরা করতে পারি. If the coils are if the coils are concentric, means they are having the same center. If the coils are concentric, then x equals to 0. মানে এটা একটা coil, এটা আরেকটা coil. These are the two coils. So therefore the center of both of them coincide. That is concentric. The centers coincide. If the coils are concentric, that is x equals to 0. So under that circumstances, the value of m will be x যদি 0 হয়ে যায়. So that will be mu 0 n1 into pi times of, this will be a cube. So pi of b square divided by 2 times of a. এটা a cube হবে, এটা a square আছে, a square and a cube gets cancels with each other to give you a. So mu 0 n1 into pi b square divided by 2a. So that is how you get the expression of this particular coil, right? So এইভাবে তুমি এই coiler expression এটা তুমি বের করতে পারো. Now you see that if I want to find, actually what did I find? I have find the flux of the second coil with respect to the first. Here I should answer a question to you which might be in your mind. So একটা question আমি এখানে answer করে দিচ্ছি যেটা তোমাদের মাথাতে আসতেই পারে. You see that actually what I am trying to find over here, আমি তো m লিখছি, but although this is m21 এটা যদিও আমি, don't write it, okay, just listen it, so don't write it. So what I have found over here is actually m21, but I write it m because somewhere I have said that m12 is equals to m21 and that can be proved. So আমরা এটা prove করতে পারি that m12 is equals to m21 and this is known as the reciprocity theorem. You will find it in your book, এটা বইয়ের মধ্যে আছে। এটাকে reciprocity theorem বলা হয়, that mutual inductance of coil 1 due to coil 2 is equals to the mutual inductance of coil 1 due to coil 2. m12 is equals to m21. আচ্ছা, এখানে অ্যাকচুয়ালি আমরা যেটা বের করেছি সেটা হচ্ছে m21. Actually what I have found is m21. Why? Because it is the flux of the second due to the current in the first. The current was in the first coil. This current was in which coil? In the coil C1. So that is why it is the flux of the second coil due to the current in the second coil. So that is, it is m21. Effect on second due to the first. Effect on second, দ্বিতীয়টার উপর effect প্রথমটার জন্য. Effect on the second due to the first. So that is why I calculate m21. তো সেইভাবে আমরা m21 টা বের করলাম. We are very happy with m21. Now instead of m21, if you have to calculate m12, যদি m21 ক্যালকুলেট না করে যদি m12 ক্যালকুলেট করতে হয়, then what will happen? Just the parameters will be changed over here. So it will be mu 0, n1 will become n2 and n2 will become n1. That's very simple. It remains invariant. n1 n2 or n2 n1 একই জিনিস. Pi also there is no alteration, but b will become a and a will become b. Are you getting it? If I want to find m12, so then mu 0 n2 n1, then pi, b will become a and a will become b. That's the change. And now you see what happens is that m12 is not equals to m21. আচ্ছা, প্রথমে এই চেঞ্জ গুলো বুঝেছো তো? b টা a হয়ে যাবে, b will become a and a will become b, because I am calculating m12. That is 2 and 1 is now interchanged. 1 আর 2 টা interchange করতে হবে. But you come out with a surprising result that m12 is not equals to m21. However, at the very beginning of the discussion of mutual inductance, I have said that m12 is equals to m21. এটা কিন্তু আমি অনেকক্ষণ আগে বলেছি, and this is a theorem which is known as reciprocity theorem. So এটা equal হওয়া উচিত, this should be equal. But in your system, you come to know that those are not equal. And the same can also be done in the solenoid system also. Solenoid mutual inductance of the, what I have calculated is mutual inductance of the secondary due to primary. That is what I have calculated. And if you calculate mutual inductance of the primary due to secondary, so then that will also come out to be unequal. এটাও unequal আসবে. Now the question is, why such things happen? Why our treatment do not agree with the general result? আমাদের এই treatment কেন general রেজাল্টের সাথে এগ্রি করে না? The reason behind this is that we have assumed something which is not perfectly real. আমরা এমন কিছু একটা assume করেছি যেটা কিন্তু পুরোপুরি সত্য নয়. We have assumed something which is not absolutely true, and that is this line, এই লাইনটা. We assume that the field is uniform throughout the cross section of C2. Now this is not absolutely true. আমরা ধরে নিয়েছি, so actually this magnetic field is where? This magnetic field is at only this particular blue point, but I have taken to be same over the entire cross section. Now this is not absolutely true. So as we are not using the true expression of the magnetic field, so that is why we are not getting that true result that M12 equals to M21. So this may be a question in your mind. So this was a question in my mind also when I have studied long before. আমি যখন পড়েছিলাম অনেক বছর আগে আমার এটা মনে হয়েছিল, I also thought that why we are not getting M12 equals to M21. So later on I came to know that this is the reason, that is why we are not getting it. So এটাই হচ্ছে কারণ যার জন্য আমরা এটা পাচ্ছি না. We assume the magnetic field to be same over the entire cross section, which is not true all the time. যেটা সবসময় কিন্তু সত্য নয়, which is not always true. And this is the reason that we are unable to get that absolute result. So সেই জন্য আমরা ওই absolute resultটা পাচ্ছি না. Is it clear to you? I hope that you have understood. In the case of this one also, এখানেও দেখো ওই কথাটা আছে. In the case of this primary secondary also, the same words has been reiterated over here. একই কথা এখানেও বলেছি. So please don't ask this question to me, I have already answered it. That M12 is not equals to M21. অনেকে আমাকে বলে, স্যার, if I have to find the mutual inductance of the first coil due to second, then what should I do? So then I just answer to them that you interchange A and B. A আর B interchange করে দাও. And as soon as they do, they ask me that, sir, you said that M12 is equals to M21, but I am not getting it. Yes, you will not get it because you have assume something which is not absolutely true, and that is why you are not getting the true general result. So I hope that this will help you to understand the things in a better way. So that was the discussion about the mutual inductances that you need to know in your this particular course.